who's next?
Cool. I'm next.
Oh, next. Now we have Alexander.
Yeah.
Dressed as Alexander.
So I'm Alexander Dijkshoorn. I'm a PhD student in the Portwings project with Stefano and with Professor Gijs Krijnen, who I think may be joining digitally, but he could not be here today. And my work is on I call it functional structures and surfaces for flapping wing aerial robotics. Basically, I look into smart materials, 3D printing of sensors and stiffness mechanisms and how to use those for the robot. So I'll shortly present the vision of what I'm doing, which I already said in one sentence. I'll give an overview of the work I did, and I'll give some preliminary results for the wind tunnel campaign we did a couple of weeks ago. So currently the robot is almost an RC plane. It flaps with its wings, but it's just steered by giving more throttle and by steering with the tail. So it's not, in that sense, it's not controlled as a bird. So what we want to do is get more sensing and actuation integrated to make full use of the rich dynamics that the flapping wings have and to understand it better. So we want to sense the deformations of the wing, we want to have some information of the flow over the wings, and we want to maybe change the stiffness of the wing during flapping to influence the wing deformation. And in my research specifically, I want to do this by embedding these things through additive manufacturing, because additive manufacturing gives the means to really gives a form freedom to shape your sensors and your structures, and it gives you the means to embed them in structures, to really make them a part of the wings. Hence, functional wing structures and surfaces. Part of my focus was on 3D printing. So if you 3D print smart materials, for example conductive materials, you print line by line, layer by layer with fused deposition modeling, which is basically a hot glue gun which extrudes a line of material. And what you get is that you get these lines, these interfaces between every line. And basically these interfaces influence the way electricity goes through the material, and they influence the way the material behaves mechanically. Because you're creating an anisotropic material. So we first studied that, showed how that works, and then we could use that in developing our sensors. So we could optimize our sensors to have a better path for the electrical current, or to actually use it to make more sensitive sensors. So if you, for example, if you take your 3D printing infill and you all point it towards something, then your current will flow through that area. So you can make areas that are more sensitive for measurement. You can make areas where the current doesn't flow. So you can really use the 3D printing to tune your sensors, so to say. And we use this to make strain sensors. We use this to make flow sensors. So for example, this is a simple piezo-resistive flow sensor. If wind hits it, it bends, and you can measure the curvature of the flap, and in that way you can determine the flow velocity, for example. Another thing we did is we have 3D printers that can print with carbon fiber, and then we can make really stiff, lightweight structures. And with this machine we can make structures that are lighter than aluminum but have the same strength, for example. So we have a higher strength to weight ratio, which is really important if you want to make something which is very strong and lightweight to fly. And the carbon fibers also have a piezoresistivity, so we could also use this structure for strain sensing. So if you just measure the resistance of the carbon fiber and it bends, the resistance changes, and that way you can use your structure, your structural element, also for sensing. So that's something very interesting that we're currently working on. We also worked on distributed active stiffness. For example, with Federico and a student of ours, we looked into just pulling on a beam. If you have a wire on the end of a beam and you pull on it, you have an actual load on the beam, and you can use this to create some, influence the active stiffness, so to say, an effective stiffness. And we came up with, Federico came up with a control law in which we could do both damping injection, or we could induce limit cycles. So we could really, by just simply pulling, changing the tension on the wire, we could really make the beam vibrate more, or we could make it stop vibrating in that way. And for torsional stiffness, I looked into frictional jamming. So if you have these they're called auxetic materials. If you have these bow ties and you pull on them, they expand in the other direction. And if you then have structures against which they jam, then you get a way wider structure which is torsionally stiffer. And in that way you could, for example, change your torsional stiffness of your wings if you embed this in the wings. Now I come to the, so this was the thing I did over the past couple of years. For this year we mainly focused on the wind tunnel campaign, of which I want to show some preliminary results for the deformation sensing. So basically, all the research so far on the robot and the modeling focused on rigid wings. Simply, you put in the kinematics at the wing base and you assume the wing is rigid, what happens? But if you look at videos, yeah, it's difficult to see in this video, but actually the wing deforms quite a lot at the end of the stroke. It's difficult to see. And one of the hypotheses people have is that this gives a more favorable angle of attack, so that this helps in the aerodynamics. And that's mainly the torsional axis, which is now at the leading edge of the wing. So the main stiffness axis, if you were to twist the wing, is at the front of the wing. That is very important for the thrust and for this deformation. And those are the two things that we wanted to study in this experimental campaign. And for this we wanted to measure the wing deformation for different wings. So yeah, I already showed you the setup. And what we have is we have these cameras, and they have an IR. It's a motion track system. It's called the OptiTrack. It has IR LEDs at every camera, which flashes, and then we have reflective markers on these wings. So they're just stickers which reflect the IR light. And then the system can completely reconstruct where the wing is, and so we can find the wing deformation and the kinematics with these markers. For the wing fabrication, basically we fabricate the robot wings with a foam cutter. It's made out of EPP foam, which is very tough foam. It's very resilient, so if you dent it or if you bend it, it goes back to its normal shape, where the standard foam that you know from packaging that breaks or that doesn't go back to its original shape. You can pass it through.
Alexander has been in wing production for a while.
Yes, I spent a month making wings. And basically the wing consists of two parts. So basically the wing consists of two parts of foam with carbon fiber reinforcement and a carbon fiber strut at the front to create the desired stiffness properties of the wing, which gives it, hypothetically gives it deformation the way it should deform, or the ideal deformation. Next to that we changed the cover of the wing, so it's now, this wing has a rubber cover, rubber paint. We also tried plastic film, which gives way stiffer wings. They don't twist that much with the plastic film. And we shifted some of the carbon reinforcements to see if the position of this torsional axis is that important. Yes, and the wings are all black because Luc does measurements with a laser, and the more reflection you have, the less information you get from the measurements. So everything is as black as we can get it. There's this black paint called Black 3.0, and apparently it's the blackest paint that you can commercially get. It's still not black enough, sadly. For the experiment I'll tell you about, I only processed part of the data, so I'll now focus on a single set of measurements. We did the experiments with the standard robot kinematics, standard robot wing, where the setup is under 5-degree angle of attack, which should be the angle of attack of the robot during flight. And we do measurements at a high wind velocity, through hole number of 0.2, and without wind to compare. And for that we analyze the effective angle of attack. Basically, like we already discussed, when you have a steady state wing, like an airplane, it's always under the same angle of attack. When you're flapping with a wing, from the wing perspective, the angle of the air is constantly changing. So this gives you a different angle of attack all of the time over a flapping period. And the way how you pitch and plunge really influences this angle of attack, and this really influences the aerodynamics around your wing. So whether there's stall or air separation or not, flow separation. So that's a really interesting parameter to analyze. And these are the raw measurements with the OptiTrack. On the left you see without wind, on the right you see with wind. And what you can already see is that there's quite some difference in the deformation of the wing. So on the left it's mainly inertial forces with a bit of added mass from the wing. And on the right there's a lot of wind. When we transform this data to the wing perspective, so now we're standing on the root of the wing, then you can see that the wing without wind deforms way more than the wing with wind. which shows us that the deformation is mainly due to wing inertia and maybe the added mass of the air. And actually having wind in the system strongly reduces the deformation of the wing. Next to that, we input the twisting and the bending in the kinematics. We input it with a 90-degree phase difference. But what you can see here, and I will replay the video for you, is that actually the twisting and the bending are now in phase instead of 90 degrees out of phase, which also seems to be due to this inertial coupling between the bending and the twisting of the wing. And if we then look at the results, if we analyze it, what we have is the amount the wing twists at half of the wing and the amount the wing bends at half of the wing. And what you see is that the twisting and the bending is indeed really in phase. And we analyzed it for no flapping, which are the circle and the black dot, and with flapping with and without wind. This is the stable position without wind. If you then turn on the wind, the wing already twists a lot. This is a sort of weather vane effect. So the wing really twists into the wind to reduce its angle of attack. If you then start flapping, you see that with wind, the stable position around which the wing flaps is also shifted compared to flapping without wind. So there's really this passive effect where the wing twists already simply due to the direction in which the average airflow is incoming. And from experiments from the fluid dynamics department, we know that in static case the wing has a stall angle of around 12 degrees. And if we now look at the effective angle of attack of the wing, so during flapping from the wing perspective, what is the effective angle with respect to the incoming flow? And you can see that it's actually, for the flexible wing, it becomes bigger than for a rigid wing. So the hypothesis that the flapping gives a more, or the flexibility gives a more effective, more favorable effective angle of attack is not true. Actually, we get a bigger angle, so we're getting closer, maybe even to flow separation, which is interesting, which is something completely different than what we expected beforehand. Yeah. So all in all, we successfully measured the wing deformation. There's a lot of data that we're currently processing. Inertia seems to dominate as wing deformation, and actually the wing flexibility mitigates offsets in the angle of attack, like the 5-degree offset at which the robot flies. We still don't fully understand or know what the effect of the lift and on the lift and the drag is. That's something we're looking into. And actually the wind reduces the wing deformation, so it seems that that's either due to added damping effects from the wind or to added stiffness effects from the wind. So it seems that either the wind is taking out energy or the wing is putting more energy into the wind. One of these two effects seems to be taking place. One thing we already saw in the measurements, when we flap with a stiffer wing that doesn't deform that much, we get way higher peak loads on the mechanism. So the mechanism has a way harder time of flapping the wing. So maybe flexibility actually gives a worse aerodynamic performance, but it gives a better mechanical performance for the mechanism. Because what we know from the current robot is that the mechanism is the main point of failure, I think we can say. It is the part that is the closest to breaking down during flying. Yeah. So I want to thank everyone with who we worked in the EU. Do you have any questions?
Thanks a lot, Alex. Peter.
Thanks, Alex. Really, very nice. I'm wondering, you said a couple of times we are processing a lot of data, and my question is, what's actually the methodology that you're using to process all this data? I mean, what are you how do you process all this data? Are you validating them against, say, analytical solution of
No. So I have all this raw data from the OptiTrack.
Yes.
And we want to get simple measures, or I think measure is the wrong term if I talk to mathematicians. We want to get simple numbers out of that to say something about the performance, right?
Yeah.
So how much does the wing bend, how much does the wing twist, and these kind of things.
So kinematic description, say.
Yeah, wing deformation in a single number expressed in a single.
Yeah, okay, and then there is another step, at least what I perceive in the conclusions that you had about it. So one thing is, okay, you have raw data and you get some kind of kinematic description.
Yeah.
Okay, and then how do you, say, do the step to to actually draw conclusions out of it? Like it's not so good for the mechanism, but for flow separation.
So what I did not present now, I still want to combine it with the data of Ricardo. So Ricardo has all this force data for the same experiment. So at the time we flapped and we measured the deformation, we also measured the forces and the torques. So we also have that data. So we also know for every measurement how much thrust was delivered, how much lift was there. So we can actually compare the deformation. We can see, okay, this was the deformation at this moment. These were the torques and the forces at the wing root.
It can be synchronized because they cannot be measured at the same time due to light.
No, we measured the forces and the deformation at the same time.
The OptiTrack.
Yes.
You didn't mention the
Yeah, but not the aerodynamics. So Luc measured the... So we have synchronized data also with forces and torques.
So when you're saying that this is not good for flow separation, it's because you have data also for the flow separation, for example.
Partly with Luc's measurements, yes.
Next talk.
Yeah.
Thanks.
Antonio.
Would it be helpful to do the same measurement in vacuum to remove it, to know what could be the inertia only effect on the...
That would be partly helpful, yes, because in the end it's a fluid-solid interaction, so it's all non-linear and it's not that simple to decouple them, let's say. But I think they tried it in the past. The main problem...
We had some measurement, but we should redo because now we can produce different stiffness. But we did the European Space Agency, we did actually measurements in flapping.
The main problem when you do that... For in this project we didn't do it. But the main...
on these wings. There is a video that you see, the pictures that I showed is actually we had the European Space Agency in vacuum, and the big problem was that these motors use a lot of power and we needed to make plates to get the heat out.
Yeah. Everything heats up in vacuum and you cannot dump your heat easily. So we cannot simply put the system in vacuum and do the measurement.
Yeah, it's more complicated than you think when doing experiments.
You suddenly run into problems that you did not expect.
Not to mention that a vacuum tank tends to be very small, and the OptiTrack system, well, you know how big it is. So.
Yeah.
No, we had with some flashing, so with that I can show you. I have videos of the experience. Well, it was actually a good learning experiment, in at least to make the measure, but these are much more precise than the measurement we did in vacuum.
And then even if you have the measurements in vacuum, can you really conclude something about that? Because it's not only you don't have a superposition of
it's difficult, it's not superposition. You cannot simply subtract it and then you only are left with one thing.
You can measure the elasticity basically, the dynamics. Yeah.
But you can use it to do a proper identification of your purely your inertial components, right?
Okay.
That's right.
Yeah.
Any other question?
Yes.
You measure the forces as function of time or cycle average?
Both.
Both.
Yeah, so we have...
As function of time.
That's what I showed in the presentation of Ricardo. What we... One moment. So
we did a lot of average.
we have them as a function of time. So this is our raw data as a function of time. So there's some noise, but if you smooth this, it's quite good raw data. And then he used this data, and then he got the averaged, periodically averaged results.
And then you see also that the time-accurate forces can be much higher than the cycle averaged force.
Yes, definitely. Yeah, because this is the cycle. These straight lines are the cycle average forces, and this is the time data. Yeah, there's a huge difference there.
Very good.
Yeah. What you could also see is that when we run into the motor limits, then you see that it starts to struggle, and you can clearly see that your average data is not that high, but the peak forces are very high on the wing. Yeah.
Thanks to the periodicity, of course, you can do very easily a lot of averaging if you are supposed that is always the same condition after steady state if we reach. So, any other questions? Otherwise, we go to the last experimental presentation and we go back to the last two theoretical things.